first production turbofan, had a bypass ratio of 0.3, similar to the modern General Electric F404 fighter engine. Civilian turbofan engines of the 1960s, such as the Pratt & Whitney JT8D and the Rolls-Royce SPI, had bypass ratios closer to 1 and were similar to their military equivalents. The first Soviet airliner powered by turbofan engines was the Tupolev Tu-124, introduced in 1962. It used the Solovyev D-20. 164 aircraft were produced between 1960 and 1965 for Aeroflot and other Eastern Bloc airlines, with some operating until the early 1990s. The first General Electric turbofan was the aft fan CJ805-23, based on the CJ805-3 turbojet. It was followed by the aft fan General Electric CF700 engine, with a 2.0 bypass ratio. This was derived from the General Electric J85/CJ610 turbojet 2850 lbf. 12,700 N, to power the larger Rockwell Sabreliner 75/80 model aircraft, as well as the Dassault Falcon 20, with about a 50% increase in thrust to 4,200 lbf, 19,000 N. The CF700 was the first small turbofan to be certified by the Federal Aviation Administration, FAA. There were at one time over 400 CF700 aircraft in operation around the world, with an experience base of over 10 million service hours. The CF700 turbofan engine was also used to train moon-bound astronauts in Project Apollo as the power plant for the lunar landing research vehicle. Common types, edit. Low bypass turbofan, edit. A high specific thrust forward/low bypass ratio turbofan normally has a multi-stage fan behind inlet guide vanes, developing a relatively high pressure ratio and, thus, yielding a high, mixed or cold, exhaust velocity. The core airflow needs to be large enough to ensure there is sufficient core power to drive the fan. A smaller core flow forward/higher bypass ratio cycle can be achieved by raising the inlet temperature of the high-pressure, HP, turbine rotor. To illustrate one aspect of how a turbofan differs from a turbojet, comparisons can be made at the same airflow, to keep a common intake for example, and the same net thrust, i.e. same specific thrust. A bypass flow can be added only if the turbine inlet temperature is not too high to compensate for the smaller core flow. Future improvements in turbine cooling forward/material technology can allow higher turbine inlet temperature, which is necessary because of increased cooling air temperature, resulting from an overall pressure ratio increase. The resulting turbofan, with reasonable efficiencies and duct loss for the added components, would probably operate at a higher nozzle pressure ratio than the turbojet, but with a lower exhaust temperature to retain net thrust. Since the temperature rise across the whole engine, intake to nozzle would be lower, the dry power fuel flow would also be reduced, resulting in a better specific fuel consumption, SFC. Some low bypass ratio military turbofans, for example F404, JT8D, have variable inlet guide vanes to direct air onto the first fan rotor stage. This improves the fan surge margin, see compressor map. 1. The widely produced Pratt & Whitney JT8D used on many early narrow-body jetliners. The fan is located behind the inlet guide vanes. 2. Solovyev D-30, which powers the Ilyushin Il-76 and Il-62M, Mikoyan MiG-31, Zion H-6K and Y-20. 3. Saturn L-31, which powers the Chengdu J-10 and J-20, Shenyang J-11, J-15 and J-16, Sukhoi Su-30 and Su-27. 4. Williams F-107, which powers the Raytheon BGM-109 Tomahawk cruise missile. 5. NPO Saturn L-55, which powers certain HAL HJT-36 Cetera. 6. Pratt & Whitney TF-30, which powers the Grumman F-14 Tomcat. 7. Eurojet EJ-200, which powers the Eurofighter Typhoon. 8. Ishikawa Harima F-3, which powers the Kawasaki T-4. 9. GTRE GTX-35 VS Cavalry, developed by GTRE. Afterburning turbofan, edit. Further information, afterburner. Since the 1970s, most jet fighter engines have been low forward/medium bypass turbofans with a mixed exhaust, afterburner and variable area exit nozzle. An afterburner is a combustor located downstream of the turbine blades and directly upstream of the nozzle, which burns fuel from afterburner-specific fuel injectors. When lit, large volumes of fuel are burnt in the afterburner, raising the temperature of exhaust gases by a significant degree, resulting in a higher exhaust velocity forward/engine-specific thrust. The variable geometry nozzle must open to a larger throat area to accommodate the extra volume and increased flow rate when the afterburner is lit. Afterburning is often designed to give a significant thrust boost for takeoff, transonic acceleration and combat maneuvers, but is very fuel-intensive. Consequently, afterburning can be used only for short portions of a mission. Unlike in the main engine, where stoichiometric temperatures in the combustor have to be reduced before they reach the turbine, an afterburner at maximum fueling is designed to produce stoichiometric temperatures at entry to the nozzle, about 2100 K, 3800 degree R, 3300 degrees Fahrenheit, 1800 degrees Celsius. At a fixed total applied fuel-air ratio, the total fuel flow for a given fan airflow will be the same, regardless of the dry specific thrust of the engine. However, a high specific thrust turbofan will, by definition, have a higher nozzle pressure ratio, resulting in a higher afterburning net thrust and, therefore, a lower afterburning specific fuel consumption, SFC. However, high specific thrust engines have a high dry SFC. The situation is reversed for a medium specific thrust afterburning turbofan, i.e., poor afterburning SFC /good dry SFC. The former engine is suitable for a combat aircraft which must remain in afterburning combat for a fairly long period, but has to fight only fairly close to the airfield, for example cross-border skirmishes. The latter engine is better for an aircraft that has to fly some distance, or loiter for a long time, before going into combat. However, the pilot can afford to stay in afterburning only for a short period, before aircraft fuel reserves become dangerously low. The first production afterburning turbofan engine was the Pratt & Whitney TF-30, which initially powered the F-111 Aardvark and F-14 Tomcat. Current low-bypass military turbofans include the Pratt & Whitney F-119, the Eurojet EJ-200, the General Electric F-110, the Plymouth Road 33, and the Saturn L-31, all of which feature a mixed exhaust, afterburner and variable area propelling nozzle. High bypass turbofan, edit. Further information, bypass ratio. To further improve fuel economy and reduce noise, almost all of today's jet airliners and most military transport aircraft, for example, the C-17, are powered by low specific thrust /high bypass ratio turbofans. These engines evolved from the high specific thrust /low bypass ratio turbofans used in such aircraft in the 1960s. Modern combat aircraft tend to use low bypass ratio turbofans, and some military transport aircraft use turboprops, No specific thrust is achieved by replacing the multi-stage fan with a single-stage unit. Unlike some military engines, modern civil turbofans lack stationary inlet guide vanes in front of the fan rotor. The fan is scaled to achieve the desired net thrust. The core, or gas generator, of the engine must generate enough power to drive the fan at its rated mass flow and pressure ratio. Improvements in turbine cooling forward/material technology allow for a higher HP turbine rotor inlet temperature, which allows a smaller and lighter core, potentially improving the core thermal efficiency. Reducing the core mass flow tends to increase the load on the LP turbine, so this unit may require additional stages to reduce the average stage loading and to maintain LP turbine efficiency. Reducing core flow also increases bypass ratio. Bypass ratios greater than 5:1 are increasingly common. The Pratt & Whitney PW1000G, which entered commercial service in 2016, attains 12.51. Further improvements in core thermal efficiency can be achieved by raising the overall pressure ratio of the core. Improvements in blade aerodynamics can reduce the number of extra compressor stages required, and variable geometry stators enable high pressure ratio compressors to work surge-free at all throttle settings. The first, experimental, high bypass turbofan engine was the AFCO-Lycoming PLF-102, a Honeywell T55 turboshaft-derived engine that was first run in February 1962. The PLF-102 had a 40 in diameter, 100 centimeters, geared fan stage, produced a static thrust of 4,320 pound, 1,960 kilograms, and had a bypass ratio of 6:1. The General Electric TF-39 became the first production model, designed to power the Lockheed C-5 Galaxy military transport aircraft. The civil General Electric CF6 engine used a derived design. Other high-bypass turbofans are the Pratt & Whitney JT9D, the three-shaft Rolls-Royce RB211 and the CFM International CFM56, also the smaller TF34. More recent large high-bypass turbofans include the Pratt & Whitney PW4000, the three-shaft Rolls-Royce Trent, the General Electric GE90/GX and the GP7000, produced jointly by GE and P&W. The Pratt & Whitney JT9D engine was the first high bypass ratio jet engine to power a wide-body airliner. The lower the specific thrust of a turbofan, the lower the mean jet outlet velocity, which in turn translates into a high thrust lapse rate, i.e. decreasing thrust with increasing flight speed. See technical discussion below, Item 2. Consequently, an engine sized to propel an aircraft at high subsonic flight speed, for example, Mach 0.83, generates a relatively high thrust at low flight speed, thus enhancing runway performance. No specific thrust engines tend to have a high bypass ratio, but this is also a function of the temperature of the turbine system. The turbofans on twin-engine transport aircraft produce enough takeoff thrust to continue a takeoff on one engine if the other engine shuts down after a critical point in the takeoff run. From that point on, the aircraft has less than half the thrust compared to two operating engines because the non-functioning engine is a source of drag. Modern twin-engined airliners normally climb very steeply immediately after takeoff. If one engine shuts down, the climb out is much shallower, but sufficient to clear obstacles in the flight path. The Soviet Union's engine technology was less advanced than the West's, and its first wide-body aircraft, the Ilyushin Il-86, was powered by low-bypass engines. The Yakov of Yak-42, a medium-range, rear-engined aircraft seating up to 120 passengers, introduced in 1980, was the first Soviet aircraft to use high-bypass engines. 1. Powerjet Sun 146 which powers Sukhoi Superjet 100. 2. General Electric CF6 which powers the Airbus A300, Boeing 747, Douglas DC-10 and other aircraft. 3. Rolls-Royce Trent 900, powering the Airbus A380. 4. Pratt & Whitney PW4000, powering the Boeing 777, MD-11 and Airbus A330. 5. The CFM56 which powers the Boeing 737, the Airbus A320 and other aircraft. 6. Engine Alliance GP7000 turbofan for the Airbus A380. 7. Aviadvigate LPS90 which powers the Ilyushin Il-96, Tupolev Tu-204, Ilyushin Il-76. 8. Lycoming ELF-502 which powers the British Aerospace 146. 9. Aviadvigate LPD-14 which will be used on the Irkut MC-21. 10. 3-shaft Progress D-436. 11. Trent 1000 powering the Boeing 787. 12. GE90 powering the Boeing 777, the most powerful aircraft engine. Turbofan configurations, edit. Turbofan engines come in a variety of engine configurations. For a given engine cycle, i.e., same airflow, bypass ratio, fan pressure ratio, overall pressure ratio and HP turbine rotor inlet temperature, the choice of turbofan configuration has little impact upon the design point performance, for example, net thrust, SFC, as long as overall component performance is maintained. Off-design performance and stability is, however, affected by engine configuration. The basic element of a turbofan is a spool, a single combination of fan forward/compressor, turbine and shaft rotating at a single speed. For a given pressure ratio, the surge margin can be increased by two different design paths. One splitting the compressor into two smaller spools rotating at different speeds, as with the Pratt & Whitney J57, or 2 making the stator vane pitch adjustable, typically in the front stages, as with the J79. Most modern Western civil turbofans employ a relatively high pressure ratio high pressure, HP, compressor, with many rows of variable stators to control surge margin at low RPM. In the 3-spool RB211 forward/Trent the core compression system is split into two, with the IP compressor, which supercharges the HP compressor, being on a different coaxial shaft and driven by a separate, IP, turbine. As the HP compressor has a modest pressure ratio, its speed can be reduced surge-free, without employing variable geometry. However, because a shallow IP compressor working line is inevitable, the IPC has one stage of variable geometry on all variants except the 535, which has none. Single shaft turbofan, edit. Although far from common, the single shaft turbofan is probably the simplest configuration, comprising a fan and high pressure compressor driven by a single turbine unit, all on the same spool. The Snecma M53, which powers Dassault Mirage 2000 fighter aircraft, is an example of a single shaft turbofan. Despite the simplicity of the turbo machinery configuration, the M53 requires a variable area mixer to facilitate part throttle operation. Aft fan turbofan, edit. One of the earliest turbofans was a derivative of the General Electric J79 turbojet, known as the CJ805-23, which featured an integrated aft fan forward/low pressure, LP, turbine unit located in the turbojet exhaust jet pipe. Hot gas from the turbojet turbine exhaust expanded through the LP turbine, the fan blades being a radial extension of the turbine blades. This arrangement introduces an additional gas leakage path compared to a front fan configuration and was a problem with this engine with higher pressure turbine gas leaking into the fan airflow. An aft fan configuration was later used for the General Electric GE36 UDF Propfan demonstrator of the early 1980s. In 1971 a concept was put forward by the NASA Lewis Research Center for a supersonic transport engine which operated as an aft fan turbofan at takeoff and subsonic speeds and a turbojet at higher speeds. This would give the low noise and high thrust characteristics of a turbofan at takeoff, together with turbofan high propulsive efficiency at subsonic flight speeds. It would have the high propulsive efficiency of a turbojet at supersonic cruise speeds. Basic two-spool, edit. Many turbofans have at least basic two-spool configuration where the fan is on a separate low-pressure, LP, spool, running concentrically with the compressor or high-pressure, HP, spool. The LP spool runs at a lower angular velocity, while the HP spool turns faster and its compressor further compresses part of the air for combustion. The BR710 is typical of this configuration. At the smaller thrust sizes, instead of all axial blading, the HP compressor configuration may be axial centrifugal, for example, CFE 738, double centrifugal or even diagonal forward/centrifugal, for example Pratt & Whitney Canada PW600. Boosted two-spool, edit. Higher overall pressure ratios can be achieved by either raising the HP compressor pressure ratio or adding compressor, non-bypass, stages to the LP spool, between the fan and the HP compressor, to boost the latter. All of the large American turbofans, for example General Electric CF6, GE90, GE9X and GX plus Pratt & Whitney JT9D and PW4000, use booster stages. The Rolls-Royce BR715 is another example. The high bypass ratios used in modern civil turbofans tend to reduce the relative diameter of the booster stages, reducing their mean tip speed. Consequently, more booster stages are required to develop the necessary pressure rise. Three-spool, edit. Rolls-Royce chose a three-spool configuration for their large civil turbofans, i.e. the RB211 and Trent families, where the booster stages of a boosted two-spool configuration are separated into an intermediate pressure, IP, spool, driven by its own turbine. The first three-spool engine was the earlier Rolls-Royce RB.203 Trent of 1967. The Garrett ATF-3, powering the Dassault Falcon 20 business jet, has an unusual three-spool layout with an aft spool not concentric with the two others. Ivchenko Design Bureau chose the same configuration as Rolls-Royce for their Lotus FD36 engine, followed by Lotus F/Progress D18T and Progress D436. The Turbo Union RB199 military turbofan also has a three-spool configuration, as do the military Kuznetsov NK25 and NK321. Geared fan, edit. Main article, Geared turbofan. As bypass ratio increases, the fan blade tip speed increases relative to the LPT blade speed. This will reduce the LPT blade speed, requiring more turbine stages to extract enough energy to drive the fan. Introducing a planetary reduction gearbox with a suitable gear ratio between the LP shaft and the fan enables both the fan and LP turbine to operate at their optimum speeds. Examples of this configuration are the long-established Garrett TFE731, the Honeywell ELF 502/507, and the recent Pratt & Whitney PW1000G. Military turbofans, edit. Most of the configurations discussed above are used in civilian turbofans, while modern military turbofans, for example, Snecma M88, are usually basic two-spool. High-pressure turbine, edit. Most civil turbofans use a high-efficiency, two-stage HP turbine to drive the HP compressor. The CFM International CFM56 uses an alternative approach, a single-stage, high-work unit. While this approach is probably less efficient, there are savings on cooling air, weight and cost. In the RB211 and Trent 3-spool engine series, the HP compressor pressure ratio is modest, so only a single HP turbine stage is required. Modern military turbofans also tend to use a single HP turbine stage and a modest HP compressor. Low-pressure turbine, edit. Modern civil turbofans have multi-stage LP turbines, anywhere from 3 to 7. The number of stages required depends on the engine cycle bypass ratio and the boost, on boosted two spools. A geared fan may reduce the number of required LPT stages in some applications. Because of the much lower bypass ratios employed, military turbofans require only 1 or 2 LP turbine stages. Overall performance, edit. Cycle improvements, edit. Consider a mixed turbofan with a fixed bypass ratio and airflow. Increasing the overall pressure ratio of the compression system raises the combustor entry temperature. Therefore, at a fixed fuel flow there is an increase in HP, turbine rotor inlet temperature. Although the higher temperature rise across the compression system implies a larger temperature drop over the turbine system, the mixed nozzle temperature is unaffected, because the same amount of heat is being added to the system. There is, however, a rise in nozzle pressure, because overall pressure ratio increases faster than the turbine expansion ratio, causing an increase in the hot mixer entry pressure. Consequently, net thrust increases, whilst specific fuel consumption, fuel flow forward/net thrust, decreases. A similar trend occurs with unmixed turbofans. Turbofan engines can be made more fuel efficient by raising overall pressure ratio and turbine rotor inlet temperature in unison. However, better turbine materials or improved vane forward/blade cooling are required to cope with increases in both turbine rotor inlet temperature and compressor delivery temperature. Increasing the latter may require better compressor materials. The overall pressure ratio can be increased by improving fan, or LP compressor pressure ratio or HP compressor pressure ratio. If the latter is held constant, the increase in HP compressor delivery temperature from raising overall pressure ratio implies an increase in HP mechanical speed. However, stressing considerations might limit this parameter, implying, despite an increase in overall pressure ratio, a reduction in HP compressor pressure ratio. According to simple theory, if the ratio of turbine rotor inlet temperature forward/HP compressor delivery temperature is maintained, the HP turbine throat area can be retained. However, this assumes that cycle improvements are obtained, while retaining the datum, HP, compressor exit flow function, non-dimensional flow. In practice, changes to the non-dimensional speed of the HP compressor and cooling bleed extraction would probably make this assumption invalid, making some adjustment to HP turbine throat area unavoidable. This means the HP turbine nozzle guide vanes would have to be different from the original. In all probability, the downstream LP turbine nozzle guide vanes would have to be changed anyway. Thrust growth, edit. Thrust growth is obtained by increasing core power. There are two basic routes available. 1 hot route, increase HP turbine rotor inlet temperature. 2 cold route, increase core mass flow. Both routes require an increase in the combustor fuel flow and, therefore, the heat energy added to the core stream. The hot route may require changes in turbine blade forward/vane materials for better blade forward/vane cooling. The cold route can be obtained by one of the following. 1. Adding booster stages to the LP forward